Okay, so in the homework, the question was um, evaluate the integral of e to the negative negative of x plus y uh, dx dy, right? This is what we want to evaluate over some region. And what was this region? The region said R is the set of xy points where x is bigger than or equal to 0, y is bigger than or equal to 0, and x plus y is less than or equal to z. Okay, so like I said on Monday, the first thing you want to do is you want to try to sketch the region. Okay, so first we try to sketch this. So the first one is the x-axis, so that's going to be on this side, y-axis, so that's over here. All right, so we know we're dealing with this region, but we have a third bound. Okay, so what's confusing about this question at first is that z, what is z? Z didn't appear anywhere else in the question, so how am I supposed to know what z is? So the way I interpreted this is z is supposed to be a surface, or if so we're integrating a surface. This is our surface, and this says that the height z typically corresponds to the height of that surface. So I'm going to assume that that's what it meant. Basically, I'm going to assume that z equals f of x, y, meaning that z equals e to the minus x plus y. Okay, so this condition right here turns into the condition that x plus y is less than or equal to um, e to the minus x plus y. Okay, so um, so here I imagine this is, I hope this is where most people got stuck. Okay, because if you got stuck here, that means you were at least on the right track. Okay, so how did I solve this? So the first thing I noticed that was kind of curious was that this and this are the same. Okay, so let's just make this look easier to work with and say like I don't know, v is less than or equal to e to the minus v, and then we can solve for v, right, and figure out what is this. Okay, so if I move this over to the other side, I have e to the v times v is less than or equal to 1. Okay, so for those of you guys who saw the hint, my hint was basically that the solution to this, or actually the solution to, where's my eraser? There we go. The solution to v e to the v equals 1. So basically, the thing that solves this, the inverse function of this, is going to be, I can write v equals w of 1. So this w is basically just, it's whatever number actually satisfies this. So I think Ethan left a comment that if you Google this, you'll find they call it like the omega constant, or someone else put the numbers like I don't remember what the number is. Um, but if you just left it as this or put it in decimal form, that's fine. But basically, to get from here to solve for v, you probably would have needed some calculator or some sort of like background knowledge. Okay. Um, so where do I go from there? So here we know that v is equal to x plus y. So I have x plus y is equal to this. Um, I'll do it like this, yeah. Equals w of 1. So that means that y, or actually we have this. So y is less than or equal to w of 1 minus x. Okay, and this right here is a line. Okay, and this is actually what I was kind of thinking would happen, right? When I saw x plus y, right? I know that like x plus y equals something is the equation of a line. So I was hoping to figure out what is x plus y equal to, and if that's equal to a constant, then I know that I have the equation of a line, meaning it's going to look something like this. Okay, and that's what I ended up with, was that this is the line y equals w of 1 minus x. Okay, so that's what this line is, and I know that the y values need to be less than this line. So I'm interested in this region. Okay, cool. So let's set up the integral. So I can integrate first with respect to y and then with respect to x, or I can do it the other way around. I'm going to do it first with respect to y. So that's e to the negative x plus y dy. So what do? I fix a value of x, right? This is just some value of x. So the minimum value of y for this value of x is going to be here at 0, right? This is the line y equals 0. And then the maximum value is going to be here on this line, right? So we're kind of looking at this region here, this strip here. So the maximum value here, what is the y value? I don't know, but it's w of 1 minus whatever x was, right? X is a constant for now. So this is the line w of 1 minus x, and that's what I want to integrate from here to here. Okay, so I don't know what that is. I need to solve it, but I know this is going to start at x equals 0, and here, well, this is the line y equals 0, so if y equals 0, we know that w of 1 minus x equals 0, so that tells me that x equals w of 1, so this is w of 1. Right, so that's this point right here. Okay, so that's what I want to integrate. Let me just copy that. Nope, copy. Okay, so this, if I want to copy it, or sorry, if I want to write this, this is dx. So now I integrate. I do the inner integral. So I still have this outer integral from x equals 0 to w of 1. This is going to be negative e to the x plus y to the negative x plus y from 0 to this. All right, and these are the values for y. So I plug those in for y, and I have the integral from x equals 0 to here of, let's see, so I have minus e to the minus x, so I distribute the negative, minus x, minus e to the minus x plus 0. Okay, so here, these x's, they cancel out, right? This is minus x, this is negative x, they cancel out, that's positive. So I have integral from 0 to here of minus e to the negative w of 1. Okay, and then, that's interesting. Okay, so, um, plus e to the negative x dx. Okay, so now I integrate these. This first one, this first term, this is just a constant with respect to x, right? There's no variables, right? This is a number, and this here is also, it's just a number. Okay, so this is going to be equal, this first one is going to be equal to minus e to the w of 1 times x minus e to the minus x from 0 to w of 1. And we plug these in, and what do we get? We have minus w of 1 e to the w of 1 um, minus e to the negative w of 1. Okay, and then we do, when we plug in 0, so this first term, when I plug in 0, we get 0. And here we get plus e to the negative 0, that's going to be 1. Okay, so there's one last simplification that I can do. So this is going to be 1. This, I'm not going to bother simplifying that. But this one I can actually simplify, because what did I say w was? I said that w was the inverse of this function. Okay, so that means that x e to the x is equal to y, but so this is the same as saying that w of y equals x, right? So it's the thing that undoes this function. Okay, so if I was to take this function and plug it in here for x, it's just going to give me y out. And that's exactly what we're doing here. Because this w function, it's the inverse of x e to the x. So this is minus, well, it's these two functions are undoing each other. So this is just going to be minus 1 minus e to the minus w1 plus 1. Those cancel. And my final answer is this. Um, I'm assuming most people would have plugged this in as, to the calculator or not known about this simplification. That's fine. If you got to this far, well, I hope you would have put that as 1. But if you got that far, great, that's going to be full credit. But that's what this w function is. It's they call it the Lambert function. It's the inverse of this function. Okay, so definitely think it was a lot harder than I think Dr. Wagner was expecting when he gave that problem. No. I highly doubt there will be a question that hard on the exam. The takeaway that I would do is, given, like a line right here, you should be able to set up this integral. Okay, and then the general idea of, how do you do this double integral, right? You evaluate this one, and then you evaluate the outer one. Let me pull up real quick the other homework questions, because actually I do want to do one of them. Here we are. Okay, so it says reverse the order of integration for this function. Okay, let me copy this. Okay, so we want to reverse the order of integration for this. So remember, I can't just flip the order of these integrals, okay? I need to understand what is the region that we are integrating over, and then rewrite that. So I'm going the other way. Okay, so let's draw this. Okay, so here I'm integrating first with respect to x. Okay, so that means I'm going to fix a value of y, and then where am I integrating from? First, I'm integrating from x equals y. Well, x equals y, that's the same as y equals x. If I draw this line, this is the line x equals y or y equals x, right? They're the same line. So that means I'm starting here. This is the minimum value of x. And then I'm going all the way up to, I'll mark it over here. This is going to be square root of pi over 2. Okay, so that's going to look something like this region. Um, and then for the y values, that means that the y values are going from 0 all the way up to root pi over 2. Okay, so this is the line y equals x or x equals y. So, and that says that, so that way we're integrating all of these strips right here. Okay, so a common mistake would be to say that we're integrating this region here, but we're not. Okay, here we're starting at y and we're going up to square root of pi over 2. We're starting at y, we're going up to square root of pi over 2. And then the y values go from 0 up to root pi over 2. So now that I have this region sketched, I want to switch the order. Okay, so let's erase these lines. I'm still interested in that same region, but now instead of fixing a value of y, I'm going to fix a value of x. Okay, so now I say, what is the minimum value of x? Oh, sorry, what is the minimum value of y? So I'm integrating first with respect to y of the same function. Okay, so the minimum value, right, of this region, that's going to be 0. And I'm going up all the way till I get to this here. And what is the y value of this? Well, I don't know, but I know this is the line y equals x. So y is going to be equal to whatever my x coordinate was that I chose. So this is all the way up to x. And then I integrate that from here to here. Okay, so the minimum value of x, that's going to be equals 0. And then Um, so that goes up to here. How do I know where this is? That's where this line is root pi over 2. So that's root pi over 2. Okay, so now I can actually integrate these. So, because before I had no clue how to integrate sine of x squared with respect to x. Okay, but if I integrate this now, I can integrate this with respect to y because this is just a constant. So it's going to be integral x equals 0 to this, and I integrate this with respect to y, so that's going to give me sine of x squared y from 0 to x dx, which is from 0 to here. So if I plug in x, I get x sine x squared, minus if I plug in 0, I just get 0. Okay, so now I integrate this, and I can actually integrate this now, right? Because now I can do a u sub, right? If I set u equals x squared, du equals 2x dx. So for the 2x dx, if I multiply by 2, multiply by 1/2, this is going to be 1/2 integral of sine u du. Okay, so I need to fix the bounds. At 0, this is 0. At square root of pi over 2. If I square that, u is going to be pi over 2. And 1/2. Integral of sine is negative cosine from 0 to pi over 2. And I get minus 1/2 cosine of pi over 2 minus 1/2 cosine of 0. Cosine of pi over 2, that's 0. Cosine of 0, that's 1. So this is going to be 1/2. Okay, so are you guys clear on how I switch the bounds? I should switch back over to the right chat. Okay, are you guys clear on how I switch the bounds? Yeah. Okay. So let's move on. I'm going to talk a little bit about applications of double integrals. Okay, so if I want to compute, let's see, so if I have some region, let's say it looks like this. Okay. Suppose I want to compute the area. Okay. What I can do is, because this might not really be like a nice function that I can integrate, like you did in Cal 2 where you had the top minus bottom, right? It might not actually be able to work out neatly like that. It might not actually be possible because I might not be able to write this as a nice function of x. Actually here, if I did something like this. Suppose I want to compute the area of something that looks like this. Okay, I couldn't write this really in that same way, but what I could do is I could think of breaking this up into a bunch of little areas, right? A bunch of little infinitely small rectangles, and then adding all of the areas of these rectangles up. Okay, so then, right, so I'm just going to add all of these rectangles up. So one thing I could do is to, right, so this area, that's going to be the integral over this whole region of dA, right? So I'm just integrating up, I'm adding up all of these areas, okay? So I'm integrating these, it's a double integral, right? 2D, I'm adding in two directions. I add them up in the x direction and I add all of them up in the y direction. So I'm just integrating an infinitely small area over my region, and we'll talk about the bounds here in a second. But if I just integrate this, it's going to give me the area of this curve, or the area bounded by this curve. Or also, actually, if instead of just area, right, if I actually said this little region has a small unit of mass, like that has a density, has a mass per unit area, right? So a density, call it rho. Then if I integrate this over all of the area, this would give me the total mass of this whole object. Okay. So let's just let me find an example for that real quick. One second.
Mic off. Mic on.
Okay. So for example, if I had the region Okay, yeah. If I had the region from -1 to 1, and then from 0 to 1. So this is going to be a nice rectangle. Okay, so this is from -1 to 1. And I'm told that the density, right, the mass per unit area, right, how dense it is depends on the square of the position. So that means that if I had like, a bunch of particles in here or something, it means that when x is bigger, it's going to be more dense. There's going to be a lot more of them, whereas when it's close to 0, it's going to be not very dense at all. Right, so the number of particles, it's a lot more dense over here, and then less dense as we get closer. Okay, so now, so here what it's telling me is that the mass isn't evenly distributed over this whole thing, right? Some areas are more dense than others, but we know how that works out. So if I want to find the total mass of this whole thing, what I can do is I can integrate this over this region, and that's going to give me the whole mass. Okay, so if I integrate the density, this is going to give me the total mass of this object. Okay, so I can set that up real quick. So this is going to be the integral. I will integrate from 0 to 1, integral from -1 to 1, x squared dx dy. Notice this doesn't depend on y at all. It's a constant, so I can bring this out. This is integral from -1 to 1, x squared dx integral 0, 1 dy. So when I integrate dy, right, this is just y from 0 to 1, which is 1. So this just depends on this integral. So this is equal to x cubed over 3 from -1 to 1 of, let's see, so that's going to be 1/3 minus, it's going to be minus -1 cubed over 3, which is 2/3. So this integral right here is going to be 2/3. So when I multiply them together, I get that the total mass of this object is going to be 2/3. Okay, so this is different from what you did in Calculus 2, if you did something similar to this in Calculus 2. Because in Calculus 2, say like when you're doing the center of mass, right? If you remember from Calculus 2, you had to find the centroid. In Calculus 2, you made the assumption that the density was constant throughout all of this and that it didn't matter, and the formulas that they gave you basically had it canceled out and it didn't matter at all. But now we can actually take that into effect by doing this double integral like this. Okay, so now we can actually generalize the idea of the centroid. So does anybody at all remember the formula for centroid? Um, does anybody remember the formula for this? I yeah, I don't blame you. Okay, so let's just revisit this real quick. If I have a scale, a balance, okay, and I add some weight on this end, and I add some weight right here on this end, right? Which way would it fall? Okay, it's probably going to fall this way, right? Assuming that these are the same weight. Just kind of because this one would have more leverage or something. So what we call this, the way we quantify this, this is what we're going to look at is kind of the torque. That's going to be the mass times the distance from the centroid, times the distance. Okay, and then so here we're going to also look at this mass times this distance. Okay, so um, they call this the moment. Okay, so this is going to be the first moment, and that's going to be kind of correspond to the torque or something that this object is feeling due to this thing. So now what if I had a bunch of these, right? So if I had another one here, another one here, and another one here, right? I'm going to need to add all of them up. So here, if I want to find, or actually, um, what I have is that if I add all these up, if I add all of these up, then then what I should get is 0. Okay, so I'm going to have some on one side and some on the other. And I can use this and I can rearrange it to get um, a formula for the center of mass. So I'm not going to do it now. I don't have time, but I'm going to make a separate video where I'm actually going to derive the formulas for the center of mass, um, so you guys can kind of see an interesting application. And I do think that is really interesting. It's just a simple double integral, but it's an actual application of where this is used. So, for example, the you would use this like this to find actually over the total mass. Right, you would use this to find the average x coordinate, and then or the center of the x coordinate of the center of mass, and then you do the same thing except with y. Over the same thing. Okay, so in when you did this in calculus 2, they gave you some, excuse me, some formula from that seemed like it came out of nowhere, and like it never makes sense. So where does the formula for this come from? But when you do it in terms of double integrals, it's actually very simple. So it's the same, right? It doesn't matter which order you integrate it in. You're going to get the same thing as long as you're careful that you write your bounds correctly, right? As long as the region that you're describing is the same, it's going to be the same integral, right? You're describing the same area, the same volume, whatever. It's going to be the same, right? It's kind of like how like when you do the derivative, right? It doesn't really matter which order you do them in, as long as you do them correctly, right? So here, this describes the same thing. Um, right? When I'm adding up a bunch of little areas, I can either add them up in the x direction first and then add those up in the y direction, like so I can add them up in the x direction and kind of get the area or the integral over this little strip, and then I add these up in the y direction, or I could do it in the y direction first and then add those strips up in the x direction. I get the same integral either way. It's just a matter of which one's more convenient for whatever you're doing. So that's why actually typically they won't write dx dy, they'll just write dA because it doesn't matter, right? It's just integrate with whatever, however is most convenient. Okay, Another interesting application. So this is how you would find the first moment, and that kind of corresponds, like I said, to the torque and to help you find the center of mass. But one thing that you can also do, and I believe most people in here are engineers of some sort, so this will be a little more useful, is if you want to find the moment of inertia, right? This is just going to be the integral of, this is going to be the second moment, so it's going to be x squared times the density um, dA. Right, so this is the moment of inertia in the x direction, and then I can do the same thing in the y direction. So this is the second moment, and this kind of corresponds to how hard it is to turn. If you're trying to twist something, how much does it resist being twisted or something like that? But now we can actually evaluate these and actually understand where do these formulas come from that they give us in physics or something. Um, so like I said, I'll do some more examples, or I'll actually work out some interesting examples like this in a separate video. But I just wanted to point them out that now we can actually evaluate these kind of questions in a more general setting. That's a lot easier, and you don't actually have to memorize any formulas for them, right? You can actually just write this down and do the integral. Okay. Also, just to emphasize the point that when we are doing this double integral, we're kind of adding up a bunch of little integrals over little areas. Okay, so if we have something that corresponds to a small area, we probably want to do a double integral of that, to get the total effect over the total area. Okay, so now let's go to triple integrals. So I don't have this anymore. So I was just saying just now that this right here, right, if this is over some region, when I integrate this, this is going to give me the area of R. Right, if I set up my bounds properly, I can do this integral. I can integrate it first with respect to x or with respect to y, doesn't matter. But if I do this integral, I get the area of R. Okay, so now if I do a triple integral, okay, so this is going to be over some region. So this is going to be, we'll call it dv. So that's going to be dx, dy, dz. So now I'm integrating in three directions, okay, over some region. So now we don't have area, we have volume. Okay, so this is going to be the volume of R. So this is actually going to let us evaluate the volume of very weird shapes. Okay, so again, we want to think of this picture, right? Where first I'm adding up these little boxes in the x direction, and then now that I have this little strip, I can do the same thing, for this strip, and I can add them all together, and this is going to give me the area. Okay, so this corresponds to first integrating with respect to y, right? I'm adding these boxes up in the y direction, and then I add those slices up in the x direction. Okay, so the the triple integral, it corresponds to the same thing, except now I have 3 dimensions. So this gave me the area of a slice, and now I can add the area of these slices up in the z direction, right, in the z direction going kind of up out of the page, to give me the volume. Okay. Um, so let me find an example and do an example, and then I think we'll be about out of time. Okay. Um, let's see. Actually, let me just do an example evaluating one. So this is from 0 to 1, 0 to z, 0 to y. Z. Okay, so this is just an example um, adding these up. Or sorry, not adding these up. This is just an example of doing these iterated integrals. Okay, so just like before, I do the innermost one first. So I'm integrating this with respect to x. So that's from 0 to 1, from 0 to z. So I integrate this with respect to x, and I get y is z x squared over 2 from 0 to y. And I end up with, so this is y cubed z over 2. Now I integrate this with respect to y and then with respect to z. So I integrate this from 0 to 1. I'm going to integrate that right now. So this is y to the 4 z over 8 from 0 to z. This is integral from 0 to 1. Plug the z in, and I get z to the 5 over 8. And then finally I integrate this. I get 1 over 8 times 6, which is 1 over 48. Okay, so working these out, if I have this, it works exactly the same. Okay, and same thing, I can switch the order of these as long as I'm very careful that the region that I describe is the same region. Okay, if there are y's or variables involved in these bounds, I have to be really careful about that. When I switch them, that I'm actually still describing the same region. Okay, if they're all constants, if it's a nice little cube that you're integrating, then you can switch them around just fine. It doesn't matter. But other than that, it works exactly the same as triple integrals. Okay. Um, so, do I have time? I have a little bit of time. Okay, so let's see. Yeah, the solid bounded by. Let's see. Nope. Okay, so it says the solid bounded by x equals y squared, and the planes z equals 0 and x plus z equals 1. Okay, so it wants me to find the volume of the solid bounded by these surfaces. Okay, so in the xy plane, right, so if this is x and this is y, this looks like this. Okay, so and if z is coming out this way, right, if this is z, then this parabola that I just drew lies in the plane z equals 0. Okay, so this is kind of like the base of our shape. and then x plus z equals 1. So that's going to look something like this. Oh, no, no, no. Hold on. Sorry. If we're in 3D, so x y squared, or x equals y squared. So that's the same for any value of z. So that's going to look like, I cannot draw this. Basically, it's going to be this, but translated the same way. So it's kind of like a long channel or something. Okay. Right? Is that what it says? It says. So I'm rereading the question. By the cylinder. Yeah. Yeah. So it's exactly. It's kind of like a half cylinder kind of thing. Okay. And then it gives me this plane. So it stops here at z equals 0. That's fine. And then it also gives me this plane z plus x equals 1. Okay, so this is just going to be kind of like, this is so hard to draw on a flat screen. It's going to kind of be like this. Let's see, so hold on. At x equals -1, z is 1. At x equals -1, z is 1, so that's up here. Okay. Yeah, so if I kind of draw this line and this line over here, that's really hard to see. But it kind of cuts this segment. That's impossible to make out when I'm drawing. Let's just go ahead and figure out how to draw this. Okay. Let's see. So here, if I want to integrate this first, let's see. First, let's integrate this with respect to. Let me rewrite this. This is going to be z equals 1 minus x. So first, let me just integrate this with respect to z, right? Because this is actually fairly obvious, right? So here, I'm going to have the integral from 0 to 1 minus x dz, right? Because I know the minimum value is 0 and the maximum value is going to be 1 minus x. Okay, so that gives me kind of in this z direction. So now I need to know, so let's integrate this with respect to, what? X? Do we want to do with respect to x? So x goes from, no, I want to do that one last. So here I'm going to go from, with respect to y. So that's going to go from negative x, negative root x all the way up to positive root x, right? Because this is the line x equals y squared. So that means y equals minus root x, and then y equals positive root x. Right, so that just integrated it this way, dy. And now I need to integrate this with respect to x. So I need to figure out what is where does this actually intersect? So the x value where this intersects, right? So z, 1 minus x, that's going to be here at 1, basically because z is 0, right? This plane 1 minus x, that's going to be 0 when x is 1. So that's x goes from here out at 0 to over here when this plane intersects the z equals 0 curve. or a z equals 0 plane to 1 dx. Okay, so I kind of just picked that one and I struggled through that one a little bit, but that's the process. Okay, you're going to try to figure out what shape does this describe and go through the bounds and figure out from I see how it's 0, but why is it 1? Okay, so this right here describes a plane that I cannot seem to draw. So at 0, it's 1. So basically the plane is going to go something like this. Okay, so I have this plane here, and it intersects the line x equals 0, right? That's this line right here, at z equals 1. And then it intersects the x-axis over here at x equals 1. Yeah, no, it's definitely hard to see. This sketch right here is a mess. Um, but so that's what makes these problems hard, is trying to visualize, what are the bounds. But if you can figure out what the bounds are, that's really all there is to these. Okay. So, and then I could integrate this. I can actually do that really quick. So, um, so here, this is going to be the integral negative root x of, integrate that with respect to z, I get 1 minus x.
Mic off. Mic on.
Okay, so then I integrate this with respect to y. So I get from 0 to 1, 1 minus x times y from minus root x to root x. That's going to be integral from 0 to 1. That's the same, so I'm going to end up with 2, 1 minus x root x dx. And then that's just a regular integral from 0 to 1. Bring the 2 out. That's root x minus x to the 3 halves. And that gives me, what? That gives me 2 times, let's see, so that's x to the, so that's 2/3 minus 2/5. 2 times 10 minus 6 over 15. Okay, so the point was, if I want the volume of this region, first thing I need to do is figure out what are the sides, the edges of my surface, of my region that I'm interested in. Okay, and then once I have that, I need to do the same thing where I integrate along one direction. I figure out what's the minimum value, what's the maximum value. So first I did from z equals 0 back here on this plane all the way up to this curve. All the way up to this plane. Okay, so from 0 to 1 minus x. And then I integrated that from down here to up here. That's not even close to the right spot. To up here. Right, so kind of along this line. And then I integrated all that with respect to x from 0 to the other edge where this plane intersects the xy plane over here at x equals 1. Okay, so once I was able to figure out those bounds, to figure out the volume of that integral, I just set this up and I integrate with respect to each of those with those bounds, and that gives me the volume. Okay, I'm going to stop the recording now.